exponential growth and exponential decay. So growth obviously is when some population of something is getting bigger, right? Decay is when it's getting smaller. So you'll just have to read the problem, the word problem, to determine is it increasing or decreasing in size to know which one of these two formulas you should use. So your exponential growth formula is going to be P times 1 plus R raised to the t power. And your exponential decay is almost exactly the same, but instead of 1 plus r, it's 1 minus r. And in this equation, that r represents the rate at which we are growing or decaying. Typically, they're going to give it to you as a percent, right? Like increasing by 50%, and then you would rewrite that percentage as a decimal, okay? And then t is going to be the amount of time that has passed while this is occurring. So maybe they say this is something that you're checking to see occurred over 10 years or 2 weeks, whatever it may be, they'll give you a time frame, okay? So, keeping that in mind, let's take a look at example A. Example A says that a species of rabbits is increasing at a rate of 7% per year. If there are currently 10,000 rabbits, how many will there be in 15 years? Okay, so if they are increasing, are we talking growth or decay? Growth. So we know we're going to use that first formula. So that P is going to be your initial amount. So for us, we know that the initial amount or the current amount of rabbits was 10,000 rabbits, right? And then that's supposed to be times 1 plus the rate at which it's changing by. They said that the rate that we were changing by was 7%. Remember, we should go and write that as a decimal. What is 7% as a decimal? Right? So 0.07 raised to the t. Remember, t is the amount of time over which this is happening. And they said this is happening over the course of 15 years. So I'm going to raise that to the 15th power. Okay. So there are no variables in what we just came up with, so you can type that into your calculator exactly as we wrote it here. So 10,000 times 1 plus 0.07 raised to the 15th power. And approximately what do we get there? Good. If we gave it as a decimal, like maybe like 0.3, 0.31, but obviously we can't have 0.3 of a rabbit, right? So we would answer this as there will be 27,590 rabbits in 15 years. Okay, let's take a look at another example. This one says a home in Melissa is currently worth $450,000. If homes in Melissa are appreciating at a rate of 2.4% per year, when will the home be worth $600,000? So even if you didn't know what appreciating meant, you can tell that it went from $450,000 to $600,000. So that means it's an increase, right? So appreciating does mean increase, depreciating would mean decrease. All right, so we already know which formula we're going to use, but this time we already know the outcome, right? So this time I know this part. So I have that 600,000 is equal to the original amount, which was 450,000, times, we said we were increasing in value, so we know we use the first formula for growth, 1 plus. They said the percent by which it was increasing was 2.4%. So what's that as a decimal? Right. But they're asking us when the home will be worth this amount. So the part we don't know is the time, right? We don't know t. That's what we're looking for, okay? So here we don't want to have to rewrite it as logarithm because we have not gone over logarithms yet. So we're going to use our calculator to help us out here. I just want two terms that I can put into my calculator. If I was trying to solve for t, I'd want to start moving stuff to the other side, right? So how could I move 450,000 to the other side? Divide, right. So I could divide both sides by 450,000 here. Those would divide out. And I also could divide out a bunch of zeros, right? These zeros would divide out, oops, and one more there. Okay, so really all that I'm now left with is 60 over 45 is equal to 1 plus 0.024 raised to the t, right? Okay, so if you want to figure out where the value of t exists, you could put this in y1 in your calculator and this in y2 in your calculator and find where they intersect, right? That should give us the value of t. So we're going to go type 60 over 45 in y1 and 1 plus 0.024 raised to the t in y2. Obviously, you don't have to use the letter t. You can use the letter x for your exponent. And we'd be looking for where these two functions would intersect at some point. So you can either pull it up in your table if you think you can find the exact point in your table, or you can just see where the two lines cross. If you're looking for where the two lines cross, remember that you can, in your calculator, use the function second trace. And I believe intersect is number 5 on the list, I want to say. Is that right? Yeah. So choose number 5. And then when it takes you back to your graph, you'll just move that flashing cursor up close to where you think that they're crossing. Press enter 3 times, and it should give you a coordinate point for where they cross. It'll probably be a decimal, but yes, they are going to cross somewhere. If you can't see where they cross and you need to change the window of your graph, you could do that as well. Okay, now remember, guys, the part we're looking for is t right here. So in the equation, in the formula, your t is like your x, and this part is like your y over here, right? So you're looking for the x value where these two intersect. So did anybody find where they intersect, the x value? Yeah. So what would it be as a decimal if we wanted to be a little more specific? 12.13? Okay, perfect. We'll say that. Okay, so we'll say in 12.13 years, homes will be worth 600,000. All right. Okay. I want you guys to try example C and D. So remember, it could be either one of the formulas up there at the top, right? Depending on if we are increasing or decreasing. You'll just plug in what they give you and solve for what they did not give you. Mm-hmm. Mm-hmm. It looks like it.
Oh, wait.
Okay, so you may have to use the table because your calculator's not calculating the intersection. So that was, what was it, 60 over 45? So 1.3 repeating, so on your, so you're going to want your table start to be at 1.33 repeating. So let's see. Yeah. So why do you have two? Should be your y. Oh, wait, okay, never mind. So we wanted to see the y value. One here. So table set. Let's do it like. Okay, so you can see the 1.3 repeating is what would give you the 12.13%. So you might just need to use your table to pull it up. All right, I think everyone was able to easily do part C because on part C they gave you all the pieces, right? So on part C, were we growing or decaying? Decaying, good. So we did use that second formula. Okay, so we had 2,500 times 1 minus, did they give us the rate on this one? Yeah, they said the rate would be 8%, so we had 0.08. And what they say the time was? 5 years. All right. So when you guys put this in your calculator, what did you guys get? All right. With change, maybe like 0.04, but if we're just going to say approximately what it would be worth, you could round to the nearest dollar. So we would say the car will be worth, did it say to round to it? No, it didn't necessarily say. Okay. So 16. All right. In 5 years. All right. Okay, for part D, what part did they not give us on part D? The rate, right. And again, on this one, we were decaying, right? So second formula. So we had 3,500 was equal to 10,000 times 1 minus r raised to the 7th power, right? Okay, so we probably divided by the 10,000. So in y1, we could have put 35 over 100. And in y2, 1 minus r to the 7, right? So here was our y1, here was our y2. We could have looked it up in the table even. What did we get as a decimal for this one? What did we get? Okay. If we kept that decimal going, it's a little bit longer, right? Like 1.3927, and it keeps going. Since it is something that's a rate, typically these are expressed as percentages, right? So I would want to go a little bit more than 2 decimals just because I want my percentage to be pretty accurate, and I'm going to have to move it over 2 places. So definitely go a few decimals past 2, okay? So our rate would then be 13.927%, right? So we can say the rate of depreciation is that 13.927%. They didn't say where to round, so nothing specific needed, but if we want to be accurate, we probably want to go more than a couple decimal places just because we're going to move it over. Okay. All right, turn it over onto the next page. Now we're going to look at the formula for half-life. So half-life is a specific type of exponential decay. So it's got a little bit different of a formula. Okay, this formula is P times 1/2 T divided by H as the exponent. T, again, just like before, is still your time over which this is occurring, while H is whatever the half-life of this particular item is. Now, if they give you the time in years, but they give you the half-life in months, you need to convert them, right? Like it says here, just make sure whatever units they give you for half-life and time, before you put it in the formula, make sure they're the same unit, okay? So let's do an example together. Example A says the half-life of carbon-10 is 20 seconds. So 20 seconds is our half-life. If you start out with 100 grams, so that's like our original piece, so this is like our P, right? How much will be left in 2 minutes? Okay, so 2 minutes would be my time. But if you notice, half-life and time were not given in the same unit, right? Half-life was given in seconds, and the time was given in minutes. And we need them to all be the same unit. So I might want to convert this 2 minutes into seconds. So what would that be? 100%. Right. And now that they're all in the same unit, we can write our formula. So we'll have the original amount, which was 100 grams, times 1/2, raised to the time, which we said was 120 seconds, over the half-life, which was 20 seconds. So we're not missing anything here. We can type this in our calculator exactly as it's written. And what do we get here? All right. So we can say the carbon 10. Oh, there will be, I guess would have been better. Let me try that again. There will be 1.56 or 563 grams of carbon 10 left. All right. Okay, let's take a look at example B. On example B, it says, how long will it take for a 40-gram sample of I-131 whose half-life is 8.040 days to decay 1/10 of its original mass? So we weren't given everything here. What are we missing? Time, right. So we'll plug in for everything else. Okay, so the final outcome is 1/10 of its original mass. So 1/10 of what was its original mass? 40. Not 1/10, sorry, 1/100th of its original mass. So 1/100th of 40. So I would have to multiply 1/100th times 40 to figure out what that would be, right? So what would that be if we multiply 1/100th times 40? Okay, so 2/5 if we're keeping fractions. Okay. All right, so I'd have 2/5 is equal to the original amount, which we again said was 40, times 1/2. You guys said we don't know T, over half-life, which they said was 8.040. Okay, now I could do exactly what we've done previously, which would be to divide by 40, right? And then this is what I would put in my Y1, and then this part here is what I would put in Y2. Again, I'm looking for where these intersect, or if we're pulling up our table, where that what amount was it? 2/5 would exist if we're trying to figure out what our X value or our T value is here. Anybody able to figure that one out, come up with where they intersect or where that will be in our table? I think I heard somebody say it. Right, 53.4, whatever it would be, days for I-131 to decay to 1/100th of its original mass. Nice. Okay. All right, flip over onto the next page, and now we're going to look at the formula for compound interest. All right, our formula for compound interest will be P times 1 plus R divided by N raised to the N times T. So R is still going to be your rate. T is still time, usually number of years. N is going to be the interest periods that occur during that year. So maybe your interest is compounded quarterly. Quarterly means how many? 4, right? Or maybe it's compounded monthly. How many months are in a year? 12. So your N would be 12. So they'll tell us in the question how often the interest is being compounded. Okay, so example A says you deposit $4,000 into an account that pays 2.92% annual interest. Find the balance after 1 year if your interest is compounded quarterly. All right, so looks like they gave us everything we would need. Our original amount, $4,000, times 1 plus the rate. What would our rate be as a decimal? 0.02. Right. And I'm supposed to divide that by N. And N is how often they are compounding the interest. And how often did they say? Quarterly, which means 4. Raised to N times T. So again, 4, right? Because the quarterly was N. And then T is over the amount of years this is happening. For us, they said just 1 year, right? So they gave me all the information. I'm just going to type that all into our calculator. And what do we end up getting? Right. So we would say the account will have $4,118.09 after 1 year. All right. Let's look at example B. Example B says we deposit $2,000 into an account that pays a 4% annual interest. Find the balance after 3 years if the interest is compounded daily. So again, it looks like they gave us everything we would need. They said we start out with how much money in the account? $2,000. So I got $2,000 times 1 plus, what's our rate? Divided by how often it's compounded. And how often did they say it's compounded? Daily. Over the course of a year, how many days are there? So I divide this by 365. Okay. And then this would be 365 times the number of years this is occurring over, which is 3. So I would just type all of that into our calculator to figure out how much will be in the account after 3 years. So how much money are we going to end up with?
$2,254 and 98 cents.
Good. So we can say there will be $2,254.98 after 3 years. Okay. All right. On example C, it says if you won $1 million in the lottery today and put it into savings for 10 years at an interest rate of 2.9%, how much would you have if your interest was compounded over these different time periods. So first is if we were compounded annually. Annually means how often? Once, just once a year, okay? Quarterly, monthly, or daily. So let's see if we can figure out what each one of these would be and which one's going to be the best deal for us. Which one would we want to use if we win the lottery? Would we want it compounded annually, quarterly, monthly, or daily? So let's see. For our annually, we'd have 1 million times 1 plus that rate. And you guys said annually meant it was only happening once. So divided by 1. And this is over the course of 10 years. So 1 times 10 would be my exponent. All right. So how much would we make if it was compounded annually? What would we have in the account now? What do we get for that first blank? Okay. Right. And right, 51 cents. Okay, awesome. All right, you guys figure out B, C, D, and then we will share our answers. So only thing that should change is that 1 that was here and here. That's the only thing that will change for parts B, C, and D, right? Good. All right, so for that quarterly, we said quarterly was how often? 4. All right, so we just plugged in 4s here and here. Can somebody tell me the amount you got for quarterly? All right. Okay, and then monthly. Monthly would mean how many times? 12. So I'm going to plug in 12s here. All right, can somebody tell me the amount that you got for monthly?
1,035,962 cents.
All right. And then finally, daily would be 365 times a year, right? And how much did we get for that one?
1,236,412.09 cents.
All right. Oops. 12 and 9 cents. So if the interest rate doesn't change, we'd be best if we were compounding daily, right? Okay. All right, flip it over onto the back page, and we're going to look at one last formula. All right, this last one is for interest that's compounded continuously. Okay, and this formula would be P times E raised to the R times T. P, again, is the principal, right, the original amount. E is the letter E or the key E on our calculator, right, like some exponential function key, all right? And then R still is your rate, T still is your time. So let's look at example A. It says you deposit $2,000 in an account that pays an 8% annual interest. Find the balance after 3 years if the interest is compounded continuously. All right, so we were given the principal amount or the original amount as $2,000. Okay, E, remember, is not something we're given. It's truly a key on our calculator. Okay, and then we should raise that to our rate times time. Well, what was our rate? 8%, right, or 0.08, times T, which they said this is occurring over the course of 3 years, right? So this is what we would put into our calculator. All right. So how much money are we going to have here? All right. Nice. Okay. All right. Last example. Example B says if the interest is compounded continuously, so lets us know that we are using this formula, at a rate of 5.12%, how long will it take for your money to double? Okay, so what are we missing here? Okay, we are missing T. They just said that they don't really care how much money. They just want to know when will your money double. Okay, so we could just use 2 to represent double and 1 to represent original, right? Okay, so we could have 2 as the outcome equals that principal, which we'll just say is 1 to show that it's doubled. E raised to our rate, which we said is that 5.12% or 0.0512 times T. Okay, so really the only thing we're missing is T. You can divide by 1, but it means the same thing, right? So basically I just need to put this in my Y1, this over here in my Y2, and figure out where do these cross or where do they intersect, whether that's on the graph or in our table. Where do we find that to happen? Very good. All right. So now we know what you would actually use these exponential functions for. We will do the practice over this tomorrow, so just make sure you bring your notes back with you so you have all the formulas down and examples of when to use them.